Hello guys, welcome to MJ School of Mining and Geology. Um, Please like, share, and subscribe, and as well comment so that we keep producing this kind of a content. Did you know that Pauling's rule have been used for decades to rationalize the crystal structure of ionic compounds? Stay tuned to hear more about this interesting topic. Well, in in 1929, the guy called Linus Pauling published a series of 5 empirical rules rationalizing inorganic crystal structures. These rules apply to inorganic compounds and describe what the preferred local environments of a cation and how these environments connect to each other. So, to understand this type of rules, you need to understand basically what we call the polyhedral elements. So when we talk about the polyhedral elements, we're going to be talking about the edges, we're going to be talking about the apex, we're going to be talking about the faces. So if we can look at this tetrahedron, remember, like I said, tetra means 4, hedron means faces. It means it has got 4 faces. Let's try to read them or count them. It's 1, it's 2, is the one at the back, which is 3, and it's at the base, it's 4, which is why we're saying it's a tetrahedron, because it has got 4 faces, which is why we say it has 4 faces. So for you to understand the Pauling's rules, you need to understand these elements. You need to understand how to count the faces, the edges, and the vertices. All right, so with the vertices or the corners, we have 1, 2, 3, 4. We've got about 4 corners or 4 vertices. And then what about the edges? Edges, we're just counting these lines. It will be 1, 2, 3, 4, 5, 6. So we've got about 6 edges. All right, so which is why we say tetrahedron. It has got about 4 faces and then 6 edges and 4 vertices. All right, thus tetrahedron can either share corner, face, or edge. All right, so when tetrahedrons are shared, we bring in the cations closer to each other. And remember, but we're gonna see with time that when the cations are brought closer to one another, there's gonna be what you call the cation repulsive force. So yeah, we know that the oxygen is the major anion in great many common minerals. All right, so it's an anion. So because oxygen has such a large electronegativity, most of the bonds in these minerals have a significantly ionic character. All right. And so then this guy Pauling's model or Linus Pauling's, he established uh, um, a series of 5 empirical rules. All right. Now these rules, they are about rationalizing inorganic crystal structures. All right. So Linus Pauling studied crystal structures and this type of and the types of bonding and coordination that occurs within them. So his studies found out that crystal structures obey the 5 rules. All right, so basically, why are these rules so important? They are important because they provide a convenient framework for examining some details of ionic structures. They are also important because they apply to ionic compounds and describe what are the preferred local environments of cation and how these environments connect to each other. They are also important because these rules can be used to explain not only crystal structures but also allow the variation in mineral composition. Now let's start with the first rule. So the first rule, it is also called what you call the radius ratio principle. So this rule states that the distance between the cation and anions can be calculated from their effective ionic radii, and that cation coordination number depends on the relative ratio of cation and surrounding anion radii. So here you can see that the cation anion distance. Remember, what is a radii? Radii is the distance from the center to the circumference of this. All right, of this ion is the distance. This has the same analogy with the radius we learned in mathematics, that the radius is the distance from the center of the circle to the circumference of that circle. So is this, if we consider these spheres, the distance from this to the circumference, all right, is what you call the radius. So if we now take the sum of the radius of the 2 spheres, this will be the sum. All right, so which is why we say, remember, the smaller one is what you call the cation, and the biggest sphere is what you call the anion. All right, so if we now take the distance is equals to the sum of the radii. So that's what Pauling's first rule is all about, which is why we're saying the distance between the cation and anion, okay, can be calculated from the total or the sum of the ionic radii. And then not only that, but the cation coordination number depends on the relative ratio of a cation surrounding an anion. So the coordination number will depend on the relative ratio of this cation, all right, and surrounding anion. So then the ratio is calculated in this way. So we say the radius of the cation divided by the radius of the anion. All right, so wherein the anion is this bigger one and then the cation is this smaller one. So that's what you call the ratio. All right, so in coordination number it's just the number of the anions that are surrounding the cation. All right, so in essence this rule says that very small cations will bond to only a few anions, while very large cations may bond to many anions. So you're going to see with good examples, and then explaining why if the cation is so small, then it means it won't touch the anions which surround it. And then if they do not touch, then that mineral structure, it becomes unstable. But if they fit tightly, if the cation fits tightly with what we call the anions, and then the mineral structure will be stable. So in other words, as the radius of the cation increases, so too will the coordination number. So the coordination number, as the coordination number increases, so it will the radius of the cation. All right. And so yes, so we define the number of large atoms that are in contact with the small atom to be a coordination number. So the number of these anions, the number of these bigger spheres which are surrounding the cation, are defined as the coordination number. All right. So for example, for a linear structure, okay, the coordination number will be 2. So it means that we have got 2 anions that surrounding the cation. Okay, so but if we have got the coordination number 3, then we say a polyhedra, and it's what you call the triangular structure, and then it means we've got 3 anions that are surrounding the cation. Okay, and so on and so on. So like I said, if we are considering this cation, so if the cation it rattles around, if it does not fit tightly, okay, it will rattle around or it will move around, and then it makes this mineral structure to become unstable. But for these two, because the cation it's tightly attached, or attached to the anions, then it becomes more stable. All right, so this one it will be moderately stable, and then this one it will be more stable. Why? Because now the cation is tightly attached to the anion surrounding it, which is why we say that this implies that if the cation surrounded by anions is too small, like this case, the structure of a mineral becomes unstable. But if it's medium sized, like this one, it will become moderately stable. And then, but if it is like this, which does not allow rattling, then it will become more stable. All right. So which is why this Pauling's model treats the anions and cations of a crystal as if they were hard spheres. You can tell it's like they are hard spheres, okay, and then they are always in contact with the smaller small radius atom, so they're always in contact. So the more the cation is in contact with all these anions, the more stable the mineral gets to become, okay, or gets to be. Now let's check. Remember the Pauling's rule, the Pauling's first rule. It talks much about we need the cation anion distance, which will give us the sum of the radius. All right. So, and then also we talk much about the coordination number. So we said the coordination number can be determined by what we call the radius ratios, right? Radius ratio, wherein we take the radius of the of the cation divided by the radius of the anion. So now let's check. So this rule implies that the different types of coordination polyhedra are determined by the radius ratio of the cation to anion. So all these anion polyhedra, and then they are determined mainly by the coordination number, and this coordination number is also determined by the radius ratio. So for example, if we've got the radius ratio that is between 0.15 to 0.22, then it means the coordination number is it's 3. Then we call that a triangular or threefold. All right, it's threefold. Now this coordination number, it just means the anions. We have got 3 anions, and if you can check here, we've got how many? This is the cation, which is at the center, and then surrounded by 3 anions. Then we count them, we say 1, 2, 3, and then it means the coordination number is 3, because the coordination number is just the number of the anions. So for the twofold coordination, it means surrounding this cation, we've got two anions, and then we say it's a linear, all right? So which is why, and then polyhedron, it's like this, and then this is triangular, which is why you see this triangular. And then for the tetrahedral, tetra means 4, and then hedral means faces. So this, we call it a fourfold coordination, because we've got 4 anions, 1, 2, 3, 4, and then it will give us the tetrahedron, which this it represents most of the silicates. So most of the actually all the silicates, they comprises the tetrahedral. All right, for example, the nesosilicates such as olivine, they've got this tetrahedron, which is just isolated, it's not bonded with anything. All right, yes. So for example, that is a tetrahedron. Then now with octahedral, that has got 6-fold coordination. It means that we've got 1, 2, 3, 4, 5, 6. All right, we've got 1, 2, 3, 4, 5, 6, and then it means what do you call? We've got 6 anions, which is why we say it's 6-fold coordination. But with a cubic, we have 8-fold coordination. With the closest packing, we've got 12 anions surrounding the cation. All right. Then now with closest packing, it means we must have the radius of around 1. Then with cubic, it should be between 0.73 to 1.00, which is what we're saying. This gives us the coordination number of the cation, which we're talking about the radius ratio. So if we know the range of the radius ratio, we can predict the coordination number. But now the coordination number is just the number of the cations, the number of the anions that are surrounding the cations. So which is why now Pauling's rule, it's about the coordination number, which is predicted by the radius ratio, and it's also about the radius or the cation anion distance, which equals the sum of all the radii. All right, so I hope it makes sense. Now with the second rule, we call this what you call the electrostatic valency principle, okay, which states that the ionic structure will be stable to an extent that the sum of the strength of the electrostatic bonds that reach an ion equal to the charge of an ion. I mean, it seems complicated, but it's not. Please stay with me, and then you're going to understand what we're talking about. All right, so remember, for example, let's look at this picture. We know that we've got the cation, at the center. Remember, this is tetrahedron. We've got the cation at the center, which is Si, and it has got 4 valence electrons. Remember, 4 plus, it's about 4 valence. It represents 4 valence electrons. All right, and then because we've got 4. And then this is the cation. Then what surrounds this cation is the anions. How many? It's 1, 2, 3, 4. Then it means the coordination number is 4, which is why CN here it's 4, because 1, 2, 3, 4. All right, and then what about this one? We've got it has got negative 2, and then it means it probably is an oxygen. It's negative 2, and then it's also, now what about the coordination number? Coordination number is 2. Now let's check something. I want to show you that when we talk about the bond strength, we're just talking about the number of the charges that are approaching the number of the charges. Can we see these arrows? They're approaching the cation at the center. So we want to check the number of charges that are approaching the cation. That's what we call the electrostatic valence, or what we call the strength of a bond. All right, this rule says that we can calculate the strength of a bond, that is its electrostatic valence, by dividing an ion's valence, all right, by its coordination number. So we care much about the ion's valence by its coordination number. The ion's valence by its coordination number. Say for instance, let's talk about the sodium chloride. All right, let's talk about the sodium chloride. So it's 1, 2, 3, 4, 5, 6. Okay, so the sodium chloride, it means it has got 6-fold coordination. All right, it has 6-fold coordination. So meaning that we know that around this cation we've got how many anions? 1, 2, 3, 4, 5, 6. So that is the coordination number. We have got 6 coordination number, which is why we write 6 here. All right, and then but now remember, we care much about what we call the cation. So what is the charge or the valence electron of the sodium, or what's in at the center? It's +1. So it means now, which is why we say, so 1/6 of a negative charge reaches the sodium ion from each chlorine. All right, so remember, in sodium chloride, each sodium is surrounded by about 6 chlorine ions. So the sodium starts in 6-fold coordination, like we said. So 1/6 of negative charges reaches the sodium ion from each chlorine. Therefore, the +1 charge on the sodium is balanced by, all right, remember the second rule. I forgot to tell you that the second rule, it's about charge neutrality. It's always about, at the end of the day, we want to make sure that the charge of the charge of this ion is equal to the charge of the cation. So now, then how do we do that? Remember, it also talk about the bond strength. So the bond strength is just about the charges that are reaching the cation. So it says that the sum of all the bonds, okay, to an ion must be equal to the charge on that ion. So it means if we were to add 1/6, 1/6, 1/6, 1/6, 1/6, 1/6, they must all give you the charge of what's at the center, that is to say +1. All right, so which is why now we say, if we've got the bond strength, remember, for this second rule, we calculate the bond strength. And how do we calculate the bond strength? We divide the ion's valence by its coordination. All right, by its coordination number. So the valence, it's 1, then we divide by its coordination number, 1, 2, 3, 4, 5, 6. Then, but remember, this now, it tells us about that the bonds, the charges that are approaching these cations, they are 1/6. Or rather, for this chlorine, we've got 1/6. For this one, 1/6. For this one, 1/6. For that one, 1/6. But now, these things, they are not, these charges, they are not balanced. All right, so the +1 charge on the sodium ion, all right, is balanced by, remember, the +1, this is -1. Okay, this is actually 1/6, so it's no longer balanced. All right, so we want to make sure that all these charges that are approaching the +1, they must be balanced. So 1/6 of a negative charge reaches the sodium ion from each chlorine. Therefore, the +1 charge on the sodium ion is balanced by, we take the coordination number of that, then multiply by the charge. Okay, the charges or the bond strength. So we take the coordination number. Remember, we are trying to balance this chlorine so that at the end of the day they become 1, so that 1 it will equal to 1 of this sodium, and then it will be balanced. So how do we balance this chlorine? We know that the charges of this chlorine which are approaching the cation, they're about 1/6, but the total the total coordination number is about, or the coordination number is 6. So we take 6 multiplied by 1/6, and then 6 will cancel 6 and will remain with only 1. Then it means the chlorine ions equal to the chlorine the sodium ions. Similarly with the CaF2 structure. So we've seen that now we've got 1, 2, 3, 4, 5, 6, 7, 8. We've got remember this is cubic, it's 8-fold coordination. But now it means here we have got 2 ions of calcium, and then 1 ion or -1, yeah, the fluorine, right? Right. So it means for every 1 calcium we need 2 of the fluorine. All right. So how would we go about that? So okay. So one thing, the first thing, we have to calculate the bond strength. We need to know the charges that are approaching the cation at the center. All right. So but if we can tell that we have got 2, and then it would be 2 divided by, let's do this, and let's do this. So it will be remember the calcium has got about valence of 2, and then how many coordination? 1, 2, 3, 4, 5, 6, 7, 8, and then it will be 8. All right, it will be 8. And then 2 divided by 8, it will just be 1/4. So it means 1/4 is all the charges that are approaching the cation from this fluorine atom. All right, from this fluorine. But now it means this thing is not balanced. Okay, remember the charge reaching this cation, okay, ion from all the fluorine ions is just 1/4. All right, but remember we've got 8 coordination. So what do? We would say 8 coordination multiplied by 1/4. Okay, 8 coordination multiplied by that that charge, and then it will just give us 2. So then it means, remember this is 2 of the fluorine. All right, so this 2 plus 2 charge, it's just equal to plus 2 charge of the calcium, then it's balanced. So it's about charge neutrality, which is why we say the strength of all this strength. Okay, so it's about all this strength, the strength of all this ionic bond. Okay, they must equal to the charge. So if we were to combine all these 1/4s, they must give you +2 at the center. That's what this rule is about. All right, this is what the second rule is all about. So let's move on. I hope it's making sense. So moving right along. All right, so we're still on the second rule. Okay, so we're trying to give you at least the last example. This is the tetrahedron. So we know we've got the oxygen surround the 4 oxygens, 1, 2, 3, 4. It means what we call the coordination number, it will be 4. So we've got about 4 coordination number, and then remember SiO4, then at the center. Okay, SiO4 to the power -4. All right, so then what about this one? All right, with this one is the first thing we calculate the coordination number. We calculate the bond strength, the number of charges that will be approaching this +4 charge. All right, the number of charges. Remember this rule, it says the sum of all these charges that are approaching the charge at the center, they must equal to this charge at the center. And if you can check, 1 + 1 + 1 + 1 is equal to 4, which is equal to this +4. It's about charge neutrality. But now, how did we come about this one? So we came up with this one by doing this. We said, okay, sharp. We know that this it's +4. Okay, so we say it's plus 4. Okay, this charge, it's plus 4, you can tell. And then what about the coordination number? It's 1, 2, 3, 4. So 4 divided by 4 is equals to 1. So it means the bond strength, or the charges that will be approaching the positive charge, or the positive cation, or the cation, or the cation, it's what you call 1, which is why we say 1, 1, 1, 1. All right, so if we combine all these things, they must give you 4. All right. But now the only problem with this one is the oxygens. Remember, this we've got 1, but remember the oxygen is -2. So, but Tina, we're having 1, 1, 1, 1, meaning that from each oxygen we're subtracting only 1. So we still remaining with -1. So for these oxygens, we still remain with -1 charge. Okay, so this -1 charge it's unpaired, it's unshared. All right, so since this -1, but you can tell that this -1, it's half of this -2. It's exactly half of this original charge. All right, so then how do we come about this? So we know now that the oxygen in the SiO4, okay, group can be just as tightly bound to ions outside the group as to the centrally coordinated Si. All right, because we've got the ones the ions, or the oxygens. Okay, some of the oxygens are not shared, and then will be able to participate in chemical reaction. All right, so basically that is that. All right, so this rule, let me take this one there. All right, so the Pauling's rule, second rule, it characterizes the minerals or the crystal structures into what you call the isosdemic, anisosdemic, and mesosdemic. All right, so the anisosdemic is the opposite of the isosdemic. All right, so let's see. In simple terms, anisosdemic crystals are those crystals in which all the bonds have got the same electrostatic valency. They have got the same electrostatic valency. And electrostatic valency, we know that it's about the bond strength. It's where you are taking the valence of that cation divided by its coordination number. We're gonna get the number. We're gonna get the electrostatic valency, or what we call the bond strength. So it means for the isosdemic, remember iso, it means the same. Okay, so I would assume asdemic, it would mean the bond strength, maybe. Okay, so but in simple terms, the isosdemic crystals, they have all the bonds having the same electrostatic valency. And if you can check here, let's go back a bit. Okay, what's happening now? It's not responding. Okay, it's fine, but I'll go back to that. So yes, so if you can remember the previous diagram, or even this one, you can check. So we've got 1, 1, 1, 1. So all of these ones, they are equal. It means all these charges that are approaching the SiO4 charge, they are of the same strength. All right. So this is isosdemic. Now with anisosdemic, it means all of these bond strength, they are not equal. It's the opposite of that one. Right? For example, this is well seen in graphite. And then with mesosdemic is about the silicate minerals. They've got what do you call the tetrahedron. And then the tetrahedron, it can either be isolated, it can either share corners, it can either share faces and many other things, and then to give us the silicate groups, so ranging from nesosilicate all the way to tetrasilicate. Remember, nesosilicate, you're talking about olivine and many others, and then we can talk about beryl and many others for what you call this cyclic structures, and then we can talk about Homer sheet of framework silicates, wherein we're talking about mica groups, and then they are weak because of the bonds are very weak. And then we can talk about lastly about matectosilicates, wherein we talk about quartz and the feldspars. All right, so all these minerals are what you call the mesosystemic. Okay, so let's do this. Right, now what about the third rule? The third rule, it's what you call the sharing of polyhedral elements. All right, number one. Then the fourth rule is what we call the sharing of polyhedral elements, number two. So it means both rule number 3 and rule number 4, they perform the same duties. All right, they perform the same duties. So it's about sharing of polyhedral elements. So basically with this rule, yeah, so how do we define that? We say in a crystal containing different cations, those with large valence and small coordination number tend not to share polyhedral elements with each other. All right, so the existence of edges and particularly faces common to coordination polyhedron decreases the stability of ionic structures. It will seem complicated by just reading that, but please do not try to cram this. Try to understand what's going on. All right, so it means one thing you should understand. Now I've learned this on a normal society, under normal circumstances, that positive will always attract negative. Okay, and then that is to say, like charges repel each other, but unlike charges attract each other. Okay, I'm talking about in normal society under normal circumstances. All right, so now, so sharing of edges of faces by a coordinating polyhedra is inherently unstable. Remember, when we first started, I said we have to understand the polyhedral elements. That is to say, the edges, the faces, the corners. All right. So when we're gonna be sharing those corners, those edges, those faces, we're gonna understand that now. For some, when we're sharing corners, we put the cations far away from each other, then avoiding what you call cation repulsive force, making now the mineral mineral structure to become stable, to become hard. But now, if we are, let's say for example, we're sharing now the faces. All right, we are sharing the faces now, and or also the faces, and also the not the vertices, but what do you call this? These ones, man. These ones. If we are sharing the let me do this. I forgot the name. If this is polyhedra, it's either we can share these ones, or we can, remember, let's say it will be here. All right, it's either we can share, yes, so it's either we can share the faces, or we can share the sides. Yes. All right, so if we're sharing the sides and the faces, what do you call them, the lines, these lines, then we make sure that now we bring the cations closer to one another, and they're going to repel each other, and it makes the mineral to become unstable. So stay tuned, let me show you what am I talking about. All right, so all right, so yes, so that's about that. So for example, let's check here. So in here, we are sharing the corners. If you're sharing the corners, you can tell that now you are putting this cation and that cation, the distance between these cations, it's broad. All right. So it means we are avoiding what you call the cation repulsion, and then it makes this mineral to become hard. All right, or to become stable. But now, if we start to share the faces, all right, if we start to share the faces and the lines, then what do we do? All right, we make sure now that we bring the cations closer to one another. But for this one, we are okay. Let's do this. Remember, we can either share the faces or the lines. The lines, we call them the edges. We can either share the faces or the edges. So, but with the vertices, when we share the vertices, right, when we share the corners, we make sure that now the cations, the cation from one polyhedra to another polyhedra, okay, they are now far away from each other. Then now, when they are far away from each other, we are avoiding what you call the we're avoiding what you call the cation repulsive force, and then we make the mineral to become stable, okay, the crystal structure. But now when we start to share the faces and the edges, then now the minerals start to become unstable, because now we bringing the cations closer to one another. So by being closer to one another, what do? They get to repel. So if we can check, this is one polyhedra, this is another one, then we are sharing this side, right? And then, but now with this one, we are sharing, we look with this one, we are sharing the edges, and then with this one, we're gonna be sharing, if you can check, it's 1 2 3, it's 4, is that one, and then this is 1 2 3 4. Can you now see? Then we are sharing this part. And then what happens, scoring, we are bringing now these cations to be unreasonably closer to one another, and then it makes the minerals to become destabilized. The mineral structure or the crystal structure becomes unstabilized and then or destabilized, and then it's no longer stable. All right, so if it's no longer stable, then the mineral structure, it becomes weak. Okay, so let's check here. For sorosilicates, we are sharing, you can tell here we are sharing these corners. For example, more epidote, more inosilicates such as more pyroxenes, you also sharing, but we are sharing the corners, but we're combining more than one polyhedron, tetrahedron. So remember, with sorosilicate, it's about two tetrahedron. With inos, what do you call this? The nesosilicate, no sharing. This polyhedral tetrahedron, it's independent. And then with cyclosilicates, tourmaline, beryl, and many others, they are having this as a cyclic structure. But with the sheets, the way they are bonding, it makes this mineral to become unstable, because now you can tell now that the charges, when you are sharing it in this way, the cations, they are brought closer to one another. It makes the minerals to become unreasonably stable. All right. Now the fourth rule, remember, we're still talking about the sharing of elements, but this is number 2. This is the simplest of them all, because it's just about, it tells you that in a crystal containing different cations, all right, in crystal containing different cations, those with large valence but now smaller coordination number, they become stingy. And then what do? They tend not to share the polyhedral elements with each other. So there is no connection of polyhedral when there is no connection of polyhedral when we have or when the crystal has large valence and smaller coordination number. So it won't share the polyhedral elements with, so these things, they won't share the polyhedral elements with each other. Remember, this one, it has got large valence 1 2 3 4 5 6, and then this one has it has a large valence. You can now see this charge is bigger, and then this one, it has got smaller coordination number 1 2 3 4. Remember, we've got 4 of these, and then it means now there is no connection between the two. Okay, so which is why we're saying no connection of polyhedra when or with the crystals which are having the large valence and the one that is having the smaller coordination number. So the Pauling's fourth rule, so it's just the extension of his third rule, stating that small cations with high charges, right? Small cations, no, where is it? Okay, this one. So this is the extension of his third, stating that small cations with large or with high charges do not share anions easily with other cations. All right, so they do not share the cations easily with other or they do not share anions easily with other cations. So this is another consequence of the fact that highly charged cations will repel each other, which is why we said both rule number 3 and 4, they can be combined because they do the same duty. They are both about minimizing the cation repulsive force, because if the cation repulsive force it's stronger, then it makes the mineral to become unstable or to become destabilized. So these rules are about minimizing the cation repulsive force, which is why we say this is another consequence of the fact that highly charged cations will repel each other. So this rule is trying to make sure that now there is no strong cation repulsive force. All right. So for example, all silicate minerals contain SiO4 tetrahedra, yet in all the many known silicate minerals, none contains SiO4 minus polyhedra that share edges or faces, because that would bring SiO4 cations too closer together, and then what will happen? What will happen is they're gonna repel one another, making now the minerals to become unreasonably stable and unstable. So this is the third rule. It's about no connection that would exist. Okay, no connection will exist when a or no connection of polyhedra with small coordination number and large valence. All right. So which is why we say in a crystal containing different cations, those with large valence and small coordination number tend not to share polyhedral elements with each other. Remember, polyhedral element, we're talking about, we can talk about the corners, we can talk about the edges, we can talk about the faces. So they do not share either their faces, they do not share either their edges, and they do not also share their corners, right? Why do they do not share these corners, vertices, or the corners, or the faces, or what we call the edges? Just because we've got now the one which has got large valence and the one that has small coordination number. So there's no connection between these two. So because there's no connection, they tend not to share anything with each other. Okay. What about the fifth rule? This is what you call the principle of parsimony. All right. So this principle is the most interesting one, because it tells us much about okay. So for example, when we to look at these two unit cells, all right. So okay, how can we put it? So we know that now crystals with unit cells that only include, okay, so the crystals with unit cells that only include one kind of coordination environment. Now look at this unit cell, they include one kind of coordination environment. Remember, all these things, they are tetrahedrons, okay? They are surrounded by four anions. It means they've got four coordination, or the fourfold coordination. So when the crystals with unit cells that only include one kind of coordination environment of chemical identical cations are gonna be more stable. These are more stable because they've got one or they've got only one kind of coordination environment of chemical identical cations. All right, so that's why they are stable. They are stable than one. They are stable than this one than this crystal with more than one coordination environment, because now look 1 2 3 4 and then 1 2 3 4 5 6. Can you see that this crystal have unit cells that have got more than one coordination environment? So this becomes unstable because we've got more than one. Their coordination environment, they're not the same. For these unit cells, for this crystal, the unit cells have got more than one coordination environment, but then then it becomes unstable. But for this one, for this crystal, the unit cells have got coordination numbers which are the same. All right. So this is the fifth rule, which predicts the number of constituents in stable crystal structures. Okay. So this principle of parsimony, it states that the number of essentially different kinds of constituents in a crystal tends to be small. All right. Remember, why the crystal or why constituents in a crystal tends to be small? Remember, we are always about saving the energy. We're always about, in chemistry, in chemistry, our goal is about minimizing the energy. So this rule is in large part because chemical systems try to, this rule is in large part because chemical systems try to minimize the energy. So why? Because when we've got the lower energy arrangement, okay, when the crystals they've got the lowest energy arrangement, okay, then it means we're gonna have more common configuration. So which is why we say the lowest energy arrangements are preferred and much more common than any other possible configuration, because we're saving energy and because they are common, they are doable. Right? So which is why we say different kind of constituents in a crystal tends to be small. All right. So we call Pauling's last rule the principle of parsimony. It states that atomic structures tend to be composed of only a few distinct components. Remember, we want to make sure that if ever, basically the aim is to have the components which are the same to minimize the energy. But if we've got different ones, they must be small. They shouldn't be many. All right. Okay, they shouldn't be many. This means that the atomic structures are relatively simple and ordered. They must be simple and ordered. It means within a unit cell, we want to see the ions that are arranged in an orderly pattern in all directions. All right. Yes, to make or to give the external appearance of that particular crystal. Okay, so they normally contain a few types of bonds and only a few types of cations or anion sites. I mean, you can see this one is not complicated. We've got just one, and then 1 2 3 4. They are not just complicated. And then this is for the ionic bonding. Remember, all the Pauling's principles, they apply in when crystals have got ionic bonds. So this is the Pauling's fifth rule. So this fifth rule predicts the number of constituents in the stable crystal structure. So according to this rule, it should hold that the number of essentially different kinds of constituents in a crystal must be small, or tends to be small, or they usually small. So the constituents here he is referring to are coordination polyhedra of a chemical identical cations. Chemical identical cations. Okay, so when he is talking about the constituents, he's talking about the coordination. He's talking about this coordination of chemical identical cations. When these cations are identical, then we want to know much about their coordination. Their coordination polyhedra. So when their coordination polyhedra are the same for these chemically identical cations, so when they are polyhedra or coordination polyhedra are the same, then it means it becomes more, this crystal structure becomes more stable. So that is the cations of the same elements and valence and their connections. So yeah, so basically these are the Pauling's rules, which are best applied in geology. And then these rules, they are very important because, for example, Pauling's rules, they can widely be used to explain not only a crystal structure, but also allowed variations in mineral composition. So this is because, for example, trace elements are present in extremely small amounts, but are often responsible for mineral color. So this is about the principle of the guy called Linus Pauling. So, ladies and gents, thank you for joining us today. It has been a great pleasure to see you today. Okay, so please don't forget to like, share, subscribe, and comment so that we keep producing this kind of a content. All right, so if you don't understand anything, if you feel you don't understand here and there, please feel free to comment or ask on the comment section, and we'll be pleased to respond to your, or to answer, or to respond to your question. Until next time, cheers.